In this video we continue our work on geometric progressions by finding the sum of a geometric sequence. In other words, we're looking at geometric series. In the previous video we looked at the example of Auntie Hayley's plan for birthday presents for her nephew Harrison, and the birthday presents were to start at £50 and increase by 5% each year until he reaches his 18th birthday. We observed that this gave us a geometric sequence with first term 50 and common ratio 1.05, and we used the summation facilities on our calculator, or the sigma facilities on our calculator, to show that the sum of all of Harrison's birthday presents up to and including his 18th birthday would be somewhere around about £1,407. We're going to now do it without needing to use the sigma functions on our calculator and develop a formula for the sum of a geometric progression. So let S18 be the sum of all of the presents that Harrison will receive from Hayley from his 1st to his 18th birthday. We've got S18 is 50, plus 50 times 1.05 is his second birthday present. 50 times 1.05 squared is his third birthday present. 50 times 1.05 cubed is his fourth birthday present, and so on all the way along to the 18th birthday present, which will be 50 times by 1.05 to the power 17. Now this sum can actually be evaluated using a fairly simple trick. We're simply going to multiply the sum through by the common ratio of the geometric progression, which is 1.05, and write down the original sum underneath. There's 1.05 times by S18, which gives me 50 times 1.05 plus 50 times 1.05 squared, all the way along to 50 times 1.05 to the power 18. We write S18 underneath it, and then we do a subtraction of the second row from the first row. On the left hand side we've got 1.05 S18, take away S18, which gives me 0.05 S18. Then, looking at the right hand side, we're going to work down column by column. So the first column I've got is 0 minus 50, which gives me minus 50. The second column gives me 50 times 1.05, take away 50 times 1.05, which gives me 0. The next column gives me 50 times 1.05 squared, take away 50 times 1.05 squared, which is also 0. All the way along until we come to the penultimate column, which gives me 50 times 1.05 to the 17, take away 50 times 1.05 to the 17, which is another 0. And then finally, I've got 50 times 1.05 to the 18, take away nothing, which gives me 50 times 1.05 to the 18. So I've got 0.05 S18 is equal to 50 times 1.05 to the 18, take away 50. In other words, we've got S18 is 50 times by 1.05 to the power 18, take away 1, divided by 0.05, which gives me £1,406.62. We can generalise this argument to give us a formula for the sum, Sn, of the first n terms of a geometric sequence with first term a and common ratio r. So Sn is a plus ar squared all the way up to ar to the n minus 2 plus final term ar to the n minus 1. We're going to multiply the sum through by r and write down the original sum underneath. R times Sn is our top line that we've just added, and Sn is just the previous line. R times Sn is ar plus ar squared all the way along to ar to the n minus 2 plus ar to the n minus 1 plus ar to the n. We're then going to do a subtraction And when we do our subtraction, we're going to get r times Sn take away Sn on the left hand side equals, from the first column we've got 0 take away a, so that's minus a. From the second column we've got ar take away ar, which is 0. The third column gives me ar squared minus ar squared, and so on all the way along until we come to the final column, which gives me ar to the n take away nothing, which is just ar to the n. So we've got r times Sn take away Sn is equal to ar to the n take away a. Doing a little bit of factorisation on the left hand side and a little bit of factorisation on the right hand side, we can write this as being Sn times by r minus 1 equals a times by r to the n take away 1. In other words, Sn must be equal to a times r to the n minus 1 divided by r minus 1. So that is our general formula for the sum of a geometric progression where we're adding n terms and the geometric progression has a common ratio of r and a first term of a. It's worth noticing that if we multiply the fraction for Sn by minus 1 over minus 1, that is the same thing as multiplying by 1, so it doesn't change the value of Sn, but it gives us a slightly different formula for Sn, which is particularly useful if the value of r lies between minus 1 and 1. So let's now start making use of this result. So our first example, we've got to find the sum of the first 12 terms of the geometric series 1.5 plus 6 plus 24 plus 96, etc. So our geometric sequence that we've got has got a first term of 1.5 and a common ratio of 4. So we can say that S12 is going to be 1.5 times by 4 to the 12 minus 1 divided by 4 minus 1. 4 minus 1 is 3. 1.5 divided by 3 is 0.5. So an equivalent form for S12 is going to be 0.5 times by 4 to the 12 take away 1. My calculator then gives me that that is 8,388,607.5. For our second example, we've got Pauline has established a fitness regime in which she will take a run each day for 6 weeks. On the first day she will run 800 meters, and on each subsequent day she will run 2% further than she did on the previous day. How far will she run on the 30th day of the regime, and what's the total distance that she will run during the 6-week regime? If dn is the distance that Pauline runs on the nth day, then we've got d1 is 800, d2 is going to be 800 times by 1.02, d3 is going to be d2 times by 1.02, and so on. So we can certainly say that the sequence d1, d2, d3, etc. is a geometric sequence with first term 800 and common ratio 1.02. The distance she runs on the 30th day will be d30, and we know that the 30th term of this GP is going to be 800, that's the first term, times by r 1.02 to the power of 30 minus 1, in other words to the power of 29. So we've got d30 is 800 times 1.02 to the power of 29, which gives me 1,420.7 meters. The total distance that she runs in the 6 weeks will be S42. That's the distance, or the sum of the distances, D1, D2, all the way up to D42, because there are 42 days in 7 weeks. Using the formula that we've got for the sum of a geometric sequence, we know that the sum of a geometric sequence is A times by r to the n minus 1, all divided by r minus 1. So in this case we've got S42 is 800 times by 1.02 to the power 42, take away 1, all divided by 1.02, take away 1, which gives me 51,890 metres. So she runs just less than 52 kilometres during the 6-week period. Our final example, we've got a geometric sequence of numbers has second term 96 and fifth term 324. We've got to find the sum of the first 15 terms of the sequence, and we then have to find how many terms of the sequence must be added together to obtain a total that exceeds 2 million. We know that the second term of this sequence is 96 and the fifth term is 324. Let's suppose that the first term is a and the common ratio is r. Then the second term of the sequence is a times r, which is 96. And the fifth term in the sequence will be ar to the 4, which has got to equal 324. If I take equation 2 and divide it by equation 1, that gives me ar to the 4 divided by ar is 324 divided by 96, which simplifies to r cubed is 27 over 8, and taking the cube root of 27 over 8, I obtain r equals 3 over 2 or 1.5. Using equation 1 now, we've got that gives me that a must be 96 divided by r, which is 64. The geometric sequence we are considering has got a first term of 64 and a common ratio of 1.5. We're looking for the sum of the first 15 terms of the sequence. We know that the sum of the first n terms of a sequence with common ratio r and first term a is given by a times r to the n minus 1 over r minus 1. So in this case, the S15 is going to be 64 times 1.5 to the power 15, take away 1, over 1.5, take away 1, which gives me 55,922.4 as the sum. For part B, if we let Sn be the sum of the first n terms, then we can write that Sn is the first term, 64, times by r to the power n, that's 1.5 to the power n, take away 1, all divided by r minus 1, which is 1.5, take away 1. So I've got 64 over 0.5, which is the same thing as 128 lots of 1.5 to the n, take away 1. So we've got to try and find the value of n, which gives me Sn being bigger than 2 million. In other words, we've got to solve the inequality. 128 times by 1.5 to the n minus 1 is greater than 2 million. If we divide each side by 128, we get 1.5 to the power n, take away 1, has got to be bigger than 15,625. In other words, we've got 1.5 to the power n must be greater than 15,626. Taking logarithms to base 1.5 to each side will give me n must be bigger than the logarithm to base 1.5 of 15,626, or n is greater than 23.82. If you haven't got logarithms to any base on your calculator, don't worry, the same thing can be achieved by taking logarithms to base 10, or indeed by taking logarithms to base e. And the box here gives you the alternative approach using logs to base 10. So what we've seen then is that the value of n must be at least 23.82, but n has got to be a whole number as far as we're concerned, so we need to take at least 24 terms and add those up to get a total that exceeds 2 million. And that concludes our look at geometric series.